Welcome and hello. This is a video exercise using HEC HMS. And in this exercise, we're going to be discussing linear reservoir base flow method. In this lesson, we'll modify the linear base flow method parameters in HMS and view simulation run results. What we see on the screen here is the web page that has the initial files as well as the instructions. The link to this page is in the description of this video. So if you want to download the files and follow along with me, you're welcome to do that. All right, I'm going to go ahead and scroll down just a little bit here. Initial baseflow.zip. The first step is to download those files before we can actually get started. Okay, those appear to be downloaded, so I'll go ahead and close that. Over here, I'll take the zip file, open it up. It says initial baseflow, and then inside that it says Poxitani. Inside that are the files that are part of the project. So I'll go up a level. Puxatani here is my project directory. I'm just going to go ahead and find where I want to put that. So I'm going to drag that folder into my target location and let that copy over and unzip for me. All right, so that's ready to go. I can now delete the zip file. Now I'm going to open up HMS. Then I'm going to open this puxatani.hms file here. So here's my HMS. I'll click on File, Open, and then Browse to that project directory. And here it is. Open, and then select puxatani.hms and select. All right, so let me open up the basin map just so we can see it on the screen here. Mahoney Creek Linear Reservoir, and here it is. I'll expand that window, and then I'm just going to zoom in a little bit. Looks like we have a bunch of different layers on. I'm going to go up to View, Map Layers, and just turn off a few of these layers. Here is our subbasin. It's a watershed with just one single subbasin element and then one sink element. The sink element here serves as a computation point. And I believe if I click on it and then click on options, I have a observed flow time series dataset, which is a discharge gauge type time series dataset, which we can use for comparison purposes. So this lesson is about the linear reservoir base flow method, which is, here's the base flow methods right down here. Before we change it to linear reservoir, we're going to run the simulation once. But just as a background, the linear reservoir base flow method assumes the base flow discharge is a linear function of the water stored in each groundwater layer. The instructions tell us to run the simulation after selecting the linear reservoir simulation here. So without going into the details about how this project is set up with regard to the transform, discretization, losses, or canopy, it just tells us to select the linear reservoir simulation and then click run. So I'm going to go ahead and click run right now. So let's go ahead and peek at the results here. I'm going to select the subbasin and then come up here to view the graph. All right, so what I have on the screen is the graph. The top plot is the hydrograph, and then below that is the hydrograph at the outlet of the subbasin. I'm not so interested in the hydrograph right now for this exercise, but the hydrograph I am for sure. What we see in black here is the observed flow I have highlighted, and then the blue line here on bottom is the model output. So I want the model output to more closely match this observed flow in black. We can look at some of the highlights of that simulation run by, again, keeping the subbasin selected and then click on this summary of results. And we have the main simulation data at the top, and then a frame for computed results, and then a frame for the observed flow. So the peak discharge that's computed was 7650, but the target peak discharge of the observed flow is 7810. So we're a little bit too low for peak flow. And then the other parameter I want to take a look at is the total discharge volume, and this is in inches. We calculated from the model it was 2.79. That's basically the sum of the direct runoff plus the base flow, 2.79 inches. And then the volume from observed that we want to match is 4.40 inches. And this is a volume because it's the 4.4 inches times the area of the watershed, which we can just click on acre feet and get the value in acre feet. So we're just going to deal with inches though. Without any base flow, we come up way short on this total discharge volume. So what we're going to do now is add base flow so that that water that infiltrates through the loss method will eventually become discharge volume here in the model and not just lost to aquifer recharge. All right, so let's go ahead and do that first. With our subbasin selected, I'm going to come down here to the components editor, and we have subbasin right here, tab selected. For Baseflow method, right now it's set to none, but I'm going to change that to linear reservoir. And now we have a Baseflow tab that appeared in the components editor. So go ahead and select that Baseflow tab. First thing we're going to do here is change the number of layers from 1 to 2. So we have the top layer, layer 1 will be our interflow, and then the layer 2, GW2, would refer to our groundwater flow. The initial type, we're going to change to discharge per area. Now, the numbers I'm getting here are in the instructions in step 5. There's a screenshot there with all the numbers. And then let's see. So for initial flow, I'm just going to set this to 0 for both layers. This is cubic feet per second per mile squared. And then the fraction, we're going to make it an equal fraction between the two layers. So 0.5 and 0.5. So all the water that's infiltrated, 50% of it will go to layer 1, 50% to layer 2, and then none for the aquifer recharge. As for the coefficient, it tells us to start with 24 and 80 hours for layers 1 and 2, respectively. And then for the number of reservoirs, we're just going to leave that at the default value of 1. So go ahead and click Save. Now let's rerun the same simulation and see what happens. Actually, if I want to look at the plot for the sink, that would not show the hyetograph. We see the plot here for just the hydrograph. Highlighted in blue is the outflow from the subbasin, and it looks like the peak is more than 9,000 CFS, which is much more than it should be here. So we're quite a bit off there. But if we want to see the base flow, we do need to actually look at the results for the subbasin. I'm going to zoom in here on this September 9th through 13th, more or less. Highlighted in blue is the results from the model, and then black is the observed flow. And I should also point out that this line down here is the base flow, this dashed maroon line. When we look at the summary report right here, we see we have way too much peak discharge, 9,369 versus our target of 7,810. However, our total volume is much closer. So we have the same 2.79 of direct runoff, but now we also included 1.46 inches of the base flow. So our total discharge, our total volume in the form of inches is 4.24, which is much closer to 4.40 on this second trial. I'll call this the second trial, even though it's the first trial using base flow. Now I'm on the web page again, and these are the results we just saw when running our trial number 2, the first trial with Baseflow. And if you're following along on the instructions, now we're on to this next task of calibrating the model, starting with step 1. It tells us that the easiest Baseflow parameter modification to make is to set the initial Baseflow at the beginning of the simulation so its results match the observed Baseflow. This change is usually only made for layer 2, which is representing groundwater, as opposed to layer 1, which is interflow. So what I'm going to do is open up that plot again and then zoom in on just the beginning of the simulation, the first few days or even first few hours, which appears I have a 0 base flow right here for the computed model results in blue right here. Barely see it. But then the black line up here is higher up. It looks like it's between 150 and 200. It looks like it's just above 150. I can come up here and look at the table results. I'll go File, Table, and then it would be this column here for observed flow. So 160, 156, and so on. So about 160, I'll say. Let me close that. So if the flow is 160 for initial base flow, and I want to change base flow tab, the initial flow, and this is, I want to change GW2 initial flow right here, but we're using CFS per mile squared. I want this to result in about 160 CFS. So to do that, I'll check the area of the subbasin itself by going to the main subbasin tab here. And it says the area is 157.27 square miles, which is almost the exact same as 160. We take 160 divided by 157, it's basically 1. So let's just set the value to 1. If I click on the base flow tab again, and then down here in GW2 initial, I'm going to change this value right here to 1. And then I'm going to save it and rerun the simulation and then see what happens, specifically focusing on those first few hours in that base flow. So let's just go straight to the plot and zoom in and see what it looks like. Okay, I'm going to zoom in on this early part here, and it looks much better. So now I'm going to highlight the model results. That's blue. And now I'm going to highlight the observed flow, which is, oh, that's the base flow. It's the same thing. And then there's the black. So there's the black, the observed flow. There's the base flow. Okay, I've zoomed in, but this is for the first 2.5, 3 days. Blue, again, is the model output. And then the black line right here is the observed flow. So it's not a perfect fit, but it's much better than when we assumed it was zero base flow through that layer 2. And our blue line was just at zero flow for the first couple days. As before, we can go ahead and look at the plot for the subbasin, the table summary. And we have 9415 as a peak flow. That's still way too much, and we should sort of expect that to happen because the only change we made was adding flow. However, the discharge for total volume is almost exactly perfect. It's 4.37 compared to 4.40. So we need to make some changes to address that peak discharge, decrease that value. The next couple steps will identify parameters to adjust, and since the linear reservoir base flow method conserves mass, then the infiltration rate should also be adjusted with some of the base flow parameters. Let's take a look at that plot one more time. I'm going to zoom in here on like September 9th through 13th. So we have too much flow during September 10th and the early part of September 11th. But then if we scroll over to the right, we actually have not enough flow from September 11th in the evening for the next few days. So what we want to do is increase the infiltration rate. That will reduce the peak flow, but it will increase the base flow contribution to the total flow and most likely more closely match the black observed hydrograph we're seeing on the plot here. So I'm going to go ahead and close this plot. Next, what we want to do is click on the loss tab and modify that infiltration rate. It's the constant rate right here. Currently, it's 0.038, so it's extremely small, but we're going to increase it up to 0.08 inches per hour. So it's still very small, but more than twice of what it was. So I'll go ahead and click Save. Another change that the instructions tell us to make is to increase the number of reservoirs for GW layer 1. That will delay the base flow peak and have a similar effect as the change we just made here of increasing the infiltration rate. So I'm going to go to the base flow tab. And then for this field here, GW reservoirs, I'm going to change the 1 to a 2 and then go ahead and click Save. Let's go ahead and run the simulation once again. Now let's go ahead and plot the graph. Here's the hydrograph right here. I'm going to zoom in on the first 10 days or so. Now our peak flow looks much better. It's not nearly as high as it was. In fact, it's a little bit too low compared to the peak of the observed flow. And what's most impressive to me is how the receding limb of the hydrograph matches almost perfectly. So now we have the computed hydrograph in blue here and the observed hydrograph in black right here. If we want to peek at the results for the summary table, we can look at those as well. Our peak discharge is 7336, which is about 500 CFS below what it should be. But then again, our peak volume of 4330.34 inches is right at 4.40 still. So that's great. Another parameter that I haven't mentioned yet is this Nash-Sutcliffe efficiency value, as well as the percent bias. And in the previous runs, we've had values around 0.7 and 0.6 for Nash-Sutcliffe, but now it's up to 0.94, which is definitely an acceptable number for most models. And this percent bias started off like 30%, but since then it's got down to single digits, so that's also sufficiently good. Another way to view results is to click on this Results tab in the Watershed Explorer and then expand our simulation runs directory and then click on September 2018 Linear Reservoir. And then we want to click on the Mahoney Creek Subbasin icon. Then what we can do if we scroll down here is select any of these time series data sets which are saved as paths in the output DSS file, such as base flow layer 1 right here. Here we have the simulation duration from September 7th through the 23rd, and then we see the flow, and this represents the base flow layer 1. If I hold down the control key on the keyboard and then click another layer like base flow layer 2, I now see that second base flow layer as a hydrograph over the same plot area. Base flow layer 1 and 2 combined would equal the main base flow layer right here. So if I add that to the plot, we now see the sum of those first three time series to equal this one here, which is a dotted line. So we have a solid line, a dashed line, and a dotted line. The instructions tell us to highlight a couple more curves. This outflow would be the sum of the base flow and the overland flow. And then the last value to select is observed flow, and that's in black here. So we've already seen some of these curves, but this is just another way to view the data. If we think the observed flow appears more like base flow layer 2 than base flow layer 1, we may want to modify the fraction of infiltrated water that goes into each layer. So let's go ahead and do that as one final trial on this exercise. And then let's navigate to our basin and then base flow tab. Now, right now for fraction, we're using 50% for layer 1 and 50% for layer 2. But for instance, if we think layer 2 more accurately represents our observed flow hydrograph, then we may want to increase this fraction to something like 0.9, representing 90% of the infiltrated water contributing to layer 2. And of course, layer 1 would have to decrease to between 0 and 0.1. I'll just say 0.1. So I'll go ahead and click Save. In fact, using this fraction allows us to remove water from the system altogether, since this linear reservoir base flow method assumes the conservation of mass. Okay, let's go ahead and save and run this simulation one last time. Okay, so that ran. We'll look at the plot. Looks good as it just did. And then if I look at the summary table here, we can get some final values for our peak discharge, which is a little bit lower than it was on the last simulation. And the total volume is also a little bit lower as well. Our percent bias actually was worse than last time, but the Nash-Sutcliffe efficiency was a little bit better. We can go ahead and play with all these parameters. In fact, that's where the instructions stop on the website. It just tells you to go ahead and modify the parameters further to increase the efficiency scores and the similarity between the computed outflow at the hydrograph and the observed flow. As a quick summary to this exercise, I have been plotting the results. So for the very first trial we ran without any base flow at all, we have the computed peak discharge in this column 4, and then we have the computed runoff in inches in this column 8, and then a couple air parameters, as well as that Nash-Sutcliffe efficiency value and the percent bias. In the next trial, we added the base flow method. In the third trial, we increased the initial inflow for layer 2, but this is the first time our percent bias dropped below 1%, which is good. However, the Nash-Sutcliffe score was still far from good. It was 0.66, and we want it to be close to 1. In the fourth trial, we increased the number of reservoirs in layer 1, and we also increased the infiltration rate, and that greatly improved our total peak discharge and hence the Nash-Sutcliffe efficiency score. And then in the final trial, we switched the fraction from 50%, 50% for layers 1 and 2, from 10% layer 1, 90% layer 2, and got some similar results as we did from trial 4. I also have a tab here in this Excel file just to keep track of the input data itself. So what you're seeing here is the 5 different trials, the infiltration rate we used for each trial, as well as the base flow parameters we used for each of the 5 trials for layer 1 and layer 2. So in yellow, I've highlighted the actual fields that changed from the previous trial, just to make it easier to identify. Well, that's all I have for this exercise on the linear reservoir base flow method in HEC HMS.